Okay, example 6-3 is about the submerged jump. So the submerged jump forms when you have tailwater larger than the conjugate depths of free jump. So a submerged jump was formed in a 1.5 meter wide horizontal and rectangular channel. So we know the width of the channel, and the channel carries a discharge of 1.45 cubic meter per second. And the water level right after the gate, so it's Y1, the water level right after the gate, and it's equal to 8 centimeter. So for a tailwater depth of Y4 equal to 1.75 meter, using the method proposed by Govinda Rao and Rajaratnam in 1963, calculate the following parameters. So the first parameter is Froude number at section 1, which is very straightforward because we have the discharge, we have Y1, so we can easily calculate Froude 1. The second question, or the second part of the question, is to calculate the submerged depth of water at the gate. So it basically looking for Y3, which is here. So we have Y1, the conjugate depths in free flow condition, Y2, water level, tailwater level, Y4, and the water level right at the gate when it's submerged is Y3. So then the question asks to calculate energy loss after the jump. So there's an equation to calculate energy loss. And you can also calculate the energy loss by writing energy equation at section 1 and section 4. So we basically do both methods. Writing energy equation would be much easier because once you have Y1 and Y4, you can easily calculate the velocity by continuity equation, and the difference would be the energy loss. We can also use the provided equation to see what is the difference. So for Froude number in rectangular cross section, we have V1 divided by square root of Y1, and we can simply use continuity equation to reduce the calculations. So we have the discharge divided by area square root of GY1, and it gives us Froude number equal to 13.64, which consider as a strong jump. So it is a strong jump if we don't have a tailwater higher than the conjugate depth. So we need to calculate the conjugate depths to see what it is. We use Belanger equation. So this is called Belanger equation. So we have all the known values except Y2, and if you calculate Y2, you'll get 1.5 meter. So in free flow condition, with the given information, the conjugate depth is 1.5 meter, but the tailwater is 1.75 meter. So you have more pressure by the tailwater level, and that's the reason it submerges the jump. So in order to calculate Y3, first we need to calculate submergence ratio. So SR is submergence ratio. So we calculate the submergence ratio. It is 0.164, and that determines that what is the degree of submergence. So the degree of submergence starts from 0 when you have free flow condition, and it can go up to a higher value when you have a highly submerged condition. For example, if the tailwater level is 5 meter, so then the value of submergence ratio can go up, and it can be larger than 1. In order to calculate Y3, we need to use the provided equation. So it's Y3 divided by A, and A is the gate opening. So as you know, the water level downstream of the gate is contracted, and we call that vena contracta, and it would be around 61% of the gate opening. So if you have a gate opening of, let's say, 10 centimeter, the water converges and Y1 is actually 6.1 centimeter. Okay, so we need to do the back calculation to find out what is the value of gate opening. And in this case, it would be 13.1 centimeter or 0.131 meter. So we can use the equation. We have all the known values. The only unknown is Y3. And if you calculate Y3, you will get 1.44 meter. So here I show you that we have Y1, 8 centimeter, Y2, 1.5 meter, Y3, 1.44, and Y4 is 1.75. You can also calculate Y0 by writing energy equation. But then you need to also assume energy loss. So this is when we get into chapter 7, when we basically go more in depth into the design of sluice gates and other type of gates, because there's an energy loss. And if you can be able to calculate the energy loss, you can calculate the Y0 as well. Okay, for the energy loss, there's an equation, and you will see that the equation is very lengthy, but we try to see what is the value of Y3. The left-hand side of this equation is known. So this is the left-hand side, is unknown, sorry, and then the right-hand side is also unknown because we don't know. I think we already calculate Y3, so it's known value. Okay, so we calculate E1 is 7.52. So delta E divided by 752 is equal to, and then I put all the values. And if you put that in Excel, or if you do the calculation, you can do it step by step. For example, you can have this would be step number 1, and then this would be the part number 2. And then this would be part number 3. Oh, sorry. Would be part number 3. So you can separately calculate them and then calculate this part and then multiply the minus and then plus here. So if you do the calculation, you will find out that the energy loss is 0.7. The energy loss ratio is 0.788, and energy loss would be an equivalent of 5.93 meter. So this, we can also calculate the energy loss by simply writing energy equation. So I can calculate velocity at section 4 or at Y4, which is Q divided by area 1.5 times Y4, and that gives me a velocity of 0.55 meter. Then I can calculate E4, which is 1.765. And then I have delta E, which is E1 minus E4, and gives me 5.75. So you can compare it with .93 meter. So pretty much close to each other. So the energy loss ratio will be 79% if you use the equation, or 76.5% if we simply use energy equation. So they are very close.